Okay, all right. So let us begin this today's session, that is session number session 7. And in this session, we are going to discuss the per unit system. So as we all know that per unit system is very important for power system engineers, and this makes the calculation simpler, and this is very much used in the our fault analysis and this load flow studies. So in GATE, you cannot find easily directly asked question on this per unit system, but this is very important. This is very basic things you should know. Otherwise, you will struck in many problems while solving the advanced problems of power system. So as we all know that this is a unitless quantity or dimensionless quantity, because if you see the definition of per unit value, this is the ratio of actual value divided by the base value. So both value numerator and denominator are in the same unit. So unit will cancel out. So it becomes dimensionless quantity. And the main advantage of this per unit system that it makes the calculation very simple, and it also makes the comparison easier. Now we can see one example here. If the actual voltage of 22 kV with base value of 11 kV is given, then what will the per unit value? It will become 2 per unit. Because you can put the value in this expression, actual value divided by base value. So actual value is 22 kV and the base value is 11 kV. So you will get easily the per unit value. And generally base values given in the problem began having given the for power and for voltage, and another base values we have to find it out. Like for power we are given the MVA rating, and for voltage we are given with the, for single phase system it is phase value, and for line to and for three phase system it is line to line voltage. And this generally be considered the rated quantity as the base quantity. So for first we will see the single phase system, and then later on we will see the three phase system. So as I told you that out of four base quantities we are given with the two base quantities, and one is apparent power base quantity and another is voltage value as the base quantity. And another base quantity we have to find it out, like current base current and the impedance base impedance. So how we can find the base current? It is simple. You have to divide the apparent base divided by the this voltage base, and you can find this base impedance. As we all know that V base divided by I base is equal to Z base, and so putting the value of I base from this expression, from the top expression, you will get the V base square divided by S base. So this is very important, and we will usually apply this, because in the problem what we have been given, we are given with the base value, voltage base and the apparent power base. So if we don't need if we don't need to find this base current, then we directly find this base impedance using this V base square divided by S base. God. Now for complex power, how we can find the active power per unit and reactive power per unit? Simply the actual values we have given, that is active power and reactive power, actual values we are given, and we have to divide it by the apparent base power that we have to consider, it is given in the problem. And for impedance, how we are going to find? We are going to having the actual quantity divided by the base quantity, so we will get the per unit impedance. Now let us see one example based on the this single phase system. In this problem, it is given that a single phase two winding transformer is rated 20 kVA, 480, 120 volts, 60 Hz. The equivalent leakage impedance of the transformer referred to the 120 volt winding denoted winding 2 is Z equivalent 2 is equal to 0.0525 at the angle of 78.13 degree ohm. Using the transformer rating as base values, determine the per unit leakage impedance referred to winding 2 and winding 1. So how we will approach this problem? So here we have to consider the base values first for finding the per unit values. Generally in this, generally in the problem, the base values are given, or you have other, if it is not given, then you have to consider that. So here in this problem, we have been given with this transformer rating as base values. So transformer rating is 20 kVA. So we have considered the apparent power rating as 20 kVA, and this 480 slash 120 volts, that is the binding, both winding side voltages. So we will consider the V base 1 as the primary voltage base is equal to 480 volt, and V base 2 as the secondary side voltage, that is equal to 120 volt. Now this equivalent leakage impedance of transformer refer to the 120 volt winding. So it is given as 0.0525 at the angle of 78.13 degree ohm. So we have to find the per unit leakage impedance referred to winding 2 and winding 1. So here for the winding 2, we have been giving the equivalent leakage impedance. So here we will first find the base impedance at the 120 volt side. So Z base 2 will be V base 2 square divided by S base, as we have seen in this expression in the last slide. So we will put these values. V base 2 will be 120 volt and S base will be 20 kVA. So you will get 0.72 ohm. Now we will apply the per unit expression, that is the actual quantity divided by base value. So actual quantity we have been given as 0.0525 at the angle this 78.13 degree and divided by 0.72. Therefore we will get this 0.0729 at the angle of 78.13 degree per unit. We have find this per unit leakage impedance referred to binding to. Now we have to find this per unit leakage impedance referred to binding one. So how we can find this value? Can anyone tell?
Sir, in per unit both are same, no, sir.
Yeah, very good. So both are same. This is the advantage of per unit values. Now if anyone wants to prove this, you can prove this also. So I have proved here. So we know that impedance referred to primary side or impedance referred to secondary side is equal to n1 divided by n2 to the whole square. So you can find this equivalent leakage impedance referred to the winding one. You will get using this expression, and you will get 0.84 at the angle of 78.13 degree ohm. This is the equivalent leakage impedance referred to the 480 volt winding. Now we will have to find this base impedance to get the per unit quantity. Therefore, we will apply this expression Z base 1 is equal to V base 1 square divided by S base. Therefore, so you will get 11.52 ohm. Now we will put this base quantity and actual quantity in the per unit expression, and you will get the answer. Z equivalent 1 per unit will be 0.0729 at the angle of 78.13 per unit. And here you can see that Z equivalent 2 is the same value. So both are equal. So this is also one advantage of using the per unit quantity. So you can say that the per unit impedance of transformer is the same whether computed from the primary or secondary side. Now we are going to see the new thing in the per unit system, that is how you can calculate the Z per unit new with the per unit given at the means older per unit quantity with the given base values for older quantity and the newer quantity also. As we all know that this Z per unit new will be Z actual divided by Z base new, and both side we take the Z base old, be just multiply or divide with by Z base old. So this first expression will become, sorry, this first expression will become Z per unit old, and this second expression just keep as it is. So you can see this you will get Z per unit new will be Z per unit old into Z base old divided by Z base new. Now we will use this expression Z base is equal to V base square divided by S base. So we are going to put here. So you will get Z per unit new will be Z per unit old multiply with Z V base old a square divided by V base new multiplied with S base new divided by S base old. Viraya, your mic is on. Please unmute yourself. Okay. So you can directly find this Z per unit at newer base by using this expression. This is also very important expression. And the proof of this expression is just one line, that is at top of the slide it is given. Now based on this expression, one problem we are going to solve, we are going to solve here. So the problem is that if Z per unit is 2 per unit on 20 kV and 100 MVA base, what is Z per unit new on 25 kV and 200 MVA base? So this is older quantity Z per unit, 2 per unit is older quantity, and this are older base 20 kV and 100 MVA, and we have to compute this base per unit impedance at the newer base quantities. So on writing this expression here, Z per unit new is equal to Z per unit old into V base square old V base square new into S base new divided by S base old. So on just putting these values, per unit impedance older value is 2 and V base old that is given 20 and V base new whole square it is 25. On multiplying with S base new, S base new is 200 MVA and S base old is 100 MVA. Simply just multiply all this expression, you will get 2.56 per unit as the answer. Till here, is there any doubt?
No, sir.
Okay. Based on this expression, directly one question asked in, it is very older problem but very basic one. 2001, it is for 2 marks. Just the previous problem, here you have to find this xd value as the for the newer base quantities, and the per unit quantity per unit quantity of xd at the older value it is given. In this question, a 75 MVA 10 kV synchronous generator has XD is equal to 0.4 per unit. The XD value in per unit to a base of 100 MVA 11 kV is. So the quantities we have given as XD per unit old, that is 0.4 per unit, V base old, that is 10 kV, and S base old, that is 75 MVA. Now we have to find this XD per unit new. We have to compute it and at the newer base quantities. So V base new is 11 kV and S base new is 100 MVA. So on putting all this quantity in this expression, you will get 0.4 multiplied with 10 divided by 11 a square into 100 divided by 75, you will get 0.4408 per unit. So this is the answer for this problem. Now we will solve this problem. This problem is asked in GATE 2010. It is for 2 marks. In this problem, we are given a power system that is given below and the specification of the components are the following. These all quantities are rated value. So for generator 1, 25 kV the rated voltage and 100 MVA is the rated apparent power. And this leakage impedance value is 9%. Sorry, this synchronous generator reactance is given as 9%, and for generator 2 similarly we are given. And for transformer and transformer 2 the reactance and this rated voltage at both binding at both binding side and this apparent power rating are given. And for line, that is for 220 volt, and the line reactance actual line reactance is given as 150 ohm. Here in this problem it is said that you have to consider 25 kV as the base voltage at generator G1 and 200 MVA as the MVA base. The impedance diagram will be. So you have to draw the impedance diagram in per unit quantities. So how you will approach that? So for the as the this transformer comes into picture, so base voltage will change according to the turns ratio. But this MVA base will not change throughout the system. So this is the important point. This S base new that we have to find the per unit reactance of whole the system based on this S base new that is given as 200 MVA. This will not change throughout the system. And since these transformers are given in the this power system, so we have to this base voltage will change as the turns ratio of the transformer changed. Now we are going to find this for G1. So we can first make the base values at every side. So it is given that V base at generator side is G1 side is given as 25 kV. And so how we can find this V base for the this line side, line 1 side? We will use the turns ratio. So here V base line will be 220 divided by 25. This is the voltage ratio, so this is the also the turns ratio into 25 kV. So this will come same 220 kV. Okay, and this will, since both transformers are identical in turns ratio, so this base at G2 will be also will be same at the G1 side. This is 25 kV. Now we will find the equivalent reactance for generator transformer, for the reactance for generator transformer in per unit value and line separately. Now first we will find for generator 1. So what are the values we have given? V base new, it is 25 kV. So I just request you all that you also try to solve parallelly with me. Otherwise, if your hand does not run here, then in exam also it will not run. So just practice here also, so that you will get compatible with the expression, and just keep it in mind. And whoever is getting answer, type your answer in the chat box. I have shown here these four options. So one option will be correct, and whoever is getting the correct answer, type your answer chat box. So older value for this base quantity we are given with J 0.09, and this V base old is 25 kV. It is same. It does not change. And this S base old is 100 MVA. So it is changed for the newer base value. So overall, this per unit value will get changed. So X per unit G1 new value will be older value multiplied with V base old whole square 25 divided by 25 whole square multiplied with S base new is 200 MVA divided by S base old, that is 100 MVA. On computing this is just get a double 0.18 per unit. So I am not writing S base new for the separately, because it will not change throughout the system. We have found for generator 1 reactance for generator 1. Now we are going to find for transformer 1. For transformer 1, X per unit T1 old is given as J 0.12, and V base older value is given as 25 kV. So we are going to find it on this primary side, this 25 kV side. You can find this reactance on any voltage side based on your assumption, based on your convenience. S base old, it is 90 MVA. So we can see that S base old get changed, and V base new is also same. V base new is 25 kV. So you will get X per unit T1 new will be X per unit T1 old multiplied with V base old whole square v base new whole square into s base new multiplied divided by s base old. So therefore x per unit t1 new will be x per unit t1 old j 0.12 v base old 25 v base new, that is 25 whole square, s base new is 200 MVA and s base old is 90. So you will get j 0.266. So it is equivalently equal to j 0.27 per unit. Now for we are going to find this per unit values for line 1. So for line 1 we are not given the per unit quantities, we are given with the actual quantity. So V base for line 1 is 220 kV and S base we know that 200 MVA. Therefore we can find first Z base. So X value is given as X value, that is actual value, is given as J 150 ohm. So first we need to find this Z base. So how we can find Z base? We know that Z base is V base a square divided by S base.
242.
Yes,
Z base 242.
what I didn't get.
Z base answer 242 ohms.
Oh, Z base you are getting 242. Yes, correct. Oh, very good. 220 whole square divided by 200. So you will get 242 ohm. And also keep in mind this uh, unit of this V base. So B base is given as in kV and S base is given MVA. So it get cancelled out. So X per unit for line will be X divided by Z base J 150 divided by 242. So it will be J 0.619 equivalently equal to J 0.62 per unit. Now for this transformer to X per unit T2 old 0.12 and V base old is 25 kV and S base old is 90 MVA and V base new is 25 kV. So it is similar to transformer 1, right? So you can directly similar values for transformer 1. So therefore you can say directly that X per unit T2 new will be X per unit T1 new, that is J 0.27 per unit. Now we are going to find for G2 So for G2, given values per unit reactance per unit value is given as J 0.09 and V base old is given as 25 kV, and apparent power older value is given as 100 MVA, and V base new will be also same 25 kV. So this will be also similar to generator 1. Therefore we can say that X per unit for generator 2 is same as for generator 1. So this is J 0.18 per unit. Now we will make this equivalent reactance diagram. So first this is generator 1 voltage. So this is reactance for G1 J 0.18, and for transformer this is J 0.27. Now we are having bus 1, and then this is bus 1, and the per unit value of reactance for line will be 0.62, and then we are with transformer 1 reactance is J 0.27, and for generator G2 it will be J 0.18. So all are in per quantities. So based on the option you can see that B is the correct option. Yes, Biraya Nagula, you are correct. Now let us see the next problem. So this problem is from GATE 2006, and this is also for 2 marks. And in this problem it is given that a generator is connected through a 20 MVA 13.8/138 kV step down transformer to a transmission line. At the receiving end of the line, a load is supplied through a step down transformer of 10 MVA 138/69 kV rating. Sorry, here it will not
That
full.
is step up transformer, sir.
Actually, the language of this problem is not that much clear. But question this it is the only question. Actually, two transformers are connected, and in between that a line is connected. So, it is supplying to the load through a step down transformer. That's why it is written like that.
In first line, sir, there
Uh,
13.8 by 138 kV step up transformer, I think, sir.
First one is step one and second one is step down.
Down.
Yeah, correct. So let me correct it. Okay, nice. Thank you. So generator is connected through a 20 MVA 13.8 138 kV step up transformer to a transmission line. At the receiving end of the line, a load is supplied through a step-down transformer of 10 MVA 138/69 kV rating. A 0.72 per unit load evaluated on load side transformer ratings as base values. So just keep this in mind. In this problem, base values are given. So first we have to find the base values. So load side transformer ratings are the base values. Is supplied from the above system for system base values of 10 MVA and 69 kV in load circuit. The value of load in generated circuit will be. So these are the newer values, and these are the older value. And this is the older per unit quantity, and this is the newer per unit base quantity. You have to find this load impedance in per unit based on the newer base quantities. This is also little bit older problem. GATE 2006. It is for 2 marks. Recently, they are not asking directly on the per unit system, but this is very helpful for solving other problems. So let us first we make the diagram, single line diagram for this system. So first we are a step up transformer which connected to transmission line. This is 13.8 138 kV, and now this line is connected to another transformer, load transformer you can say, and this is load. So this transformer rating is 138/69 kV, and apparent power rating is 20 MVA, and this transformer apparent power rating is 10 MVA. So this load is given at 0.72 per unit at the base quantities. So we can say that given values are Z per unit old is 0.72 per unit, and S base old 10 MVA, and V base old is 69 kV. So we need to find this load impedance at the generator circuit. So S base new will be S base new will be, this is generator circuit, so S base new will be 20 MVA, and V base new will be 13.8 kV. Now we will apply this expression, Z per unit new is equal to Z per unit old multiplied with V base old divided by V base new into S base new S base old. So we will get Z per unit at newer base quantity will be Z per unit old is 0.72, V base old is 69 divided by 13.8 whole square. It will be S base new is 20 and S base old is 10 MVA. So it will be 0.72 5 square 25 multiplied with 2, it will be 36 per unit. So answer will be A. Yes, Biraya Nagula, you are correct. Very good. You have, I think you have gave answer for all the problems that I solved. So now we can move to the next part for three-phase system. This is very important. Single phase system we have seen. Now we are going to see the three-phase system. So in generally three-phase system, the base quantities we are always given for apparent power base quantity always given as three-phase power, and base quantity we are given for line-to-line voltage. So not we are given for single phase power or phase voltage. It is always given as line voltage or three phase power, three phase base power in the problem. And the balance three phase circuit can be solved in per unit on a per phase basis after calculating delta load into equivalent star load. So we will consider, we will solve the problems like if we have a delta load. So first we will convert to a star load, and then we will do the per phase, we will solve that problem as per phase basis, and uh, we can convert the per phase system into the per unit system also based on the convenience. So now these quantities are given, so we can find the another quantities also. So so for power system, we are four base quantities: apparent power base quantity, and this voltage quantity, and then current quantity and impedance quantity. So but in three phase system, we have to consider this single phase and line to neutral, that is phase base quantity also. So for single phase base quantity, base apparent power will be, it will be divided by three phase base apparent power divided by 3. And if you find the phase voltage, uh, base phase voltage, so you have to divide the line to line base voltage by root 3. So this will give you the base value in line to neutral voltage. And now for the current quantity, the base current quantity will be S base single phase divided by B base line neutral. And if you write it in three phase form, then S base three phase divided by root 3 into V base line to line. So from both you will get the same answer. And now for Z base, how you are going to solve? So in the problem, always the impedance values are given in per phase. So we are going to consider this base value also in per phase. So base value of impedance in per phase will be V base line to neutral divided by I base. Now we are going to put this I base value, that is S base single phase divided by V base line neutral from the upper expression, from this expression. So we will get V base square line neutral divided by S base single phase. Now we can put this V base ln value, that is V base LL divided by root 3 whole square, you will get this one. And S base single phase will be S base 3 phase divided by 3. So you will get V base LL square divided by S base 3 phase. So in the problem we are given with this S base 3 phase and V base LL. So you need to just keep this in mind. Per phase base quantity impedance will be V base LL whole square divided by S base 3 phase. You don't need to convert in phase voltage or single phase apparent power. You will directly get the per phase base impedance like this. Just like at the single phase system. For three phase system, you have to put this line voltage and the total three phase power, total three phase apparent base power. And similarly, you can find this per unit value for active and reactive power by dividing this actual quantity divided by with this three phase base power. And for impedance, we will divide the actual quantity by this base quantity. You will get the per unit value for resistance and reactance. So there are three key points for three phase system, and that is also important, but this is generalized one. If you understood these points in this slide, then you can understand these points also. First point is that line to line voltage in per unit is always equal to phase voltage in per unit. So if you are given with line to line voltage in per unit, then it is also equal to line to neutral voltage in per unit. How you can prove this? You can prove by this expression. So you can write per unit voltage in line to line will be actual voltage in actual line to line voltage divided by the base line to line voltage, and just put all these values in the line to neutral value, that is root 3 times of phase voltage, and the base quantities you can also write like this, and you will get the root 3 will cancel out, you will get the V per unit same as the per unit in line to neutral voltage. And the second point is that two base values given are almost equal to S base 3 phase and V base LL. So as I told you, in the problem always given the base quantities, that is three phase apparent power and this line to line voltage. So you have to consider this as base quantity and this line to line voltage as the base quantity. And the third key point is that all base impedances are given as per phase impedance for three base system. So in the problem always this base impedance are given in per phase. So we have to consider this per phase base impedance also for finding this per unit quantity. Now we are going to solve the problem based on this three phase system. So this is the last problem. You all of you can try this problem. So here the question is that a three-phase star connected load is drawing power at a voltage of 0.9 per unit and 0.8 power factor lagging. The three-phase base power and base current are 100 MVA and 437.38 ampere respectively. The line-to-line voltage in kV is. So base power and this base current are given. So given values are S base three phase, that is given as 100 MVA, and I base is given as 437.38 ampere. Now you will apply the previous and the expression that we have seen in the slide. Brian Nagula, you have any doubt? You have raised
No,
your
no,
hand.
no, sir.
Okay. So we have seen that S base three phase this one we are going to use this expression because we are given with I base and we need to find V base LL. So we need to find line to line base voltage. It is not given. So first we will find this line to line base voltage. So we know that S base 3 phase will be root 3 times V base line to line into I base. One can use the line to neutral base voltage also, but the expression will get changed. So if you are using the line to neutral voltage, then in the place of root 3, it will be 3 times.
3.
Yeah, correct. So 100 into 10 to the power 6 root 3 times root I base will be 437.38. So we will get
132 kilowatt.
V base LL as 132 kilovolt. Right. Now we know that we have to find the actual voltage and this per unit value you are given. So we know we are given with per unit value that is given as 0.9. So we can write V per unit is V actual LL divided by V base LL. If you are using like here one wants to use the line to neutral voltage, so both numerator and denominator will be in line to neutral voltage or phase voltage. So accordingly you can use the expression. So it will be 0.9. We need to find the actual voltage divided by base value is 132. We have found here. So V actual LL will be 118.8 kV. This is the answer. 118.8 kV. So for three-phase system, many person get confused. I just want to tell you that just keep in mind these things. You will never get confused. And also keep in mind these three important points.
Sir, for star to delta also same formula, sir.
What?
Uh, Star to delta.
A star to delta you have to analyze this Z base how you can write. This is you have to convert it into delta to star. That will but we will consider for a star system also because in that system only V base LL is root 3 times of V base phase voltage and line voltage is equal to phase voltage. So that's why we have considered this a star connected system. For that
Okay.
generally we will not take as the a standard. Generally we take the standard for the star system. So that's why we have expressed all the expression in this thing.
Okay, sir.
So any other doubt?
Sir, once go to that problem, sir. 11th slide. Problem.
Yeah,
Sir, here transformer voltages are there, no, sir. 138 kV, 138 kV.
yeah,
Secondary and primary.
yeah.
If that are different, sir, what will be happen, sir?
What?
In network, in power system network, same voltages will be not there, no, sir. One transformer will have some voltages, other transformer will have other voltages.
So you are saying that this transformer has uh, here this load side will also 13.8 kV. You are saying that?
No, sir, no, sir. Here,
Then
first transformer 13.8 by 138 kV.
yeah,
If second transformer has 140 by 70 kV, sir.
140 by 70. Okay, so that is the
Sir.
rating of transformer, but
Yes, sir.
that is rating of transformer, but the voltage will be decided by this transformer only. That is connected to generator, because the generator is the active source. So it will decide the voltage, and this rating of transformer decides the voltage level, what will be the actual voltage level. And the rating of transformers, it also denotes the turns ratio. Means here
Yes,
this
sir.
here this sorry, here this voltage level is given, so you can find this turns ratio V1 V2 divided by N1 N2. So suppose this generator 1 is not able able to able to supply the voltage at 13.8 kV. So at the primary it will not 13.8 kV, it will be a different voltage. Suppose this generator is providing power at 12 kV, so this side will be 12 kV. And how much voltage at this side? Can anyone tell? If generator is supplying power at 12 kV, then what will be the voltage at this side, this line side?
120
12,
kV.
Yeah. So that is the thing. They are providing the turns ratio in the by giving the voltage level. That if you are providing this voltage at this primary side, then the secondary side voltage will be this. So these are the rated values, and this is the rated apparent power, and this is the rated apparent power.
Then second transformer also changes, sir. That ratings.
So yeah, so here 120 kV you are getting at this voltage level. Then certainly in practical system there will be some drop through the line. Then here you will not get 120 kV. Suppose you are getting 115 kV or 112 kV. So accordingly you will get here a different voltage level. So how much voltage level you get here? So V load will be
55, 52.5 kV, sir. 52.
V load will be 16 into 115 divided by 138. This much voltage you are getting here. So practical system generally we have different scenario, but in the problem we have to go through the what they are saying.
Sir,
Yeah.
sir, will you share this PDF on WhatsApp group or not? Sir, I want to take a screenshot of the formulas. Some of you share in this PDF.
Okay. So you can go through this what this YouTube channel. There I have shared these slides. I am not in WhatsApp group,
Okay, sir.
so I am sharing you the link. So you can go through this YouTube channel, and there you can find these recordings, and in the description box you can find the link for slide. Okay.
Okay, sir. Thank you, sir.
Hmm. Thank you all for joining, and we will meet in the next session. Thank you all.
thank you, sir.
Next section topic, sir.